so far, talking about AI and robotics and this new track, which is AI for materials. We are very honored to, of course, talk about the next theme, which is building self-driving labs, which is a practical introduction. And for our next topic, we will give you a glimpse into the core components behind self-driving labs in hardware and software. I'm very, very curious to learn more. So please, of course, put your hands together, supported by EDB and A-Star. It is a pleasure to invite on stage Dr. Muhammad Jaral, Director of Engineering from Accelerated Materials, to give his presentation. Please give him a warm welcome.
Oh, cool. Okay, hi everyone. So yeah, thank you for that very kind introduction. So yeah, I'm Mohammed. I'm Director of Engineering here at Accelerated Materials. And today I'll be talking to you a little bit about approaches beyond AI. So Professor Ryan and a lot of my esteemed speakers before me have spoken about the wonderful ways in which AI can be used to accelerate materials discovery. But at the end of the day, our materials discovery processes ultimately need data. We're working at the cutting edge, and often we're dealing with phenomena which are difficult to predict, and we need experimentation in order to provide the data that we need in order to reach our desired goals. So today, I'll be giving you some introductory tips on how you can implement intelligent automation processes to help accelerate your materials discovery processes. So I'll just be giving you a brief introduction into implementing automation today. And if you have any further questions on implementing laboratory automation, on using AI and machine learning, then please do take a snapshot of my email, and please do get in touch with me. I'd be more than happy to answer any questions. For those of you who don't know me, I'm Director of Engineering at Accelerated Materials. I've also been a research fellow at the University of Cambridge for the last 7 years, and I've been working on developing automated systems on machine learning for over a decade now. And yeah, it's a pleasure for me to share some of my knowledge with you today. So to give you a bit of background on the company, Accelerated Materials is a spin-out from the University of Cambridge. We're commercializing 7 years of R&D here in order to help bring you these automation technologies and the technologies in our machine learning processes. We offer a range of software, development services, but today is going to be less about our products and more about me giving you just some tangible, useful, introductory information on implementing automation in your own labs. So I know that many of you here are from various different industries across the globe. Whether you're doing decarbonization, you're trying to cure the world of new diseases, or you're trying to develop next generation batteries, ultimately, new materials are what unlock new capabilities in all of these fields. And I know that when all of you in your various industries are attempting to develop these new materials, you often hit the same stumbling blocks, because at the end of the day, chemistry is chemistry. And materials R&D can be really challenging. So for instance, for those of you who are developing a material, often it's not just a case of finding the right pressure or the temperature. Often you'll have a multi-step process. Within each step, you're going to have your own solvents, its catalysts, bases, ligands, and something as simple as just changing one solvent can affect the entire process where you need to redo your whole optimization. In something like a multi-step optimization process, where you have multiple solvents, catalysts, bases, pressures, temperatures, if you try to test all of these combinations, ultimately you're going to be doing thousands or millions of reactions. And modern R&D is quite expensive. Labs cost money, chemicals cost money, scientists cost money, and it's just not feasible for you to categorically test all of these combinations. If we're being honest with ourselves, a lot of materials today are developed just by scientists in white coats. You're mixing chemicals in a lab, iteratively trying things, and after weeks and months, you receive a result which you eventually hope will work. And a lot of these AI technologies are still very much in their infancy. And we live in a world now where it's not just enough for you to maximize the yield of your material. A lot of us have shareholders where we need to reduce the cost of our syntheses. Regulatory is becoming increasingly important where we're pushed to do green synthesis. And these multi-objective optimizations just add to the complexity of the problem. So we have our traditional scientist who's wearing his lab coat using these traditional methods. often the type of approach that you might adopt is you might take a single variable like temperature, you will do your experiment at various temperatures, find the best temperature, fix your optimization of that process, and then move on to the next variable, which might be concentration or time. This works okay when you've got 3 or 4 variables, but let's say you've got a very complex process with 20 or 30 variables. Suddenly you're doing thousands of reactions, and it's not very feasible for you to go through them all. Discrete choices. So for something like pressure or temperature, you can model a mathematical relationship between your temperatures. But let's say you're trying to pick a solvent. How do you get an AI system to understand what the difference, say, between hexane or ethanol is? Dynamic adaptation. So a lot of these optimization processes can be quite static, where you're given a grid of experiments to do at the start, you go through that entire grid of experiments, but you're not really making use of the data that you've got in the past. And I've already spoken about multiple objectives. And as my colleagues have spoken about before me, AI is a fantastic way for you to help reduce the number of experiments that you need and make smart decisions when you're trying to optimize your chemical processes. And the way in which I discuss AI and automation in this presentation is just one way in which you can use AI. And as my colleagues have mentioned, there are a multitude of ways in which you can use AI and machine learning for the development of materials. Let's say that you have a wealth of data on reactions that you've done in the past. You can build a neural network, or you can fire up a decision tree, just give it your data and help it to give you new reaction conditions for the reactions that you'll run in the future. There have been decades and decades of research in the literature, in journal articles, in scientific publications on reactions that people have done in the past. And there are data mining tools available that can troll through all of that literature and give you information on the processes that you want to run to help speed up your optimizations. And generative models. I know some people love them, some people hate them, some people think they're amazing, some people think they're overhyped. Regardless of what your opinions are, they do have some genuinely tangible applications in the field of materials discovery. One of the ways in which we've used them in accelerated materials is very early in the development process, where when we're trying to come up with novel processes for materials, we can look at the ways in which people have done various reactions in the past, and then the generative models are able to bring these approaches together to come up with something novel that we can then try to optimize through a different process. But we still sometimes have the problem that I spoke about at the beginning of the presentation. When we're dealing with something like chemical reactivity, where we're dealing with chemicals that haven't been used in the literature before, or we're trying to do reactions which haven't been done in the literature before, a lot of the time these phenomena are just not known about, and they can be very difficult to predict. Because chemistry is difficult. Data sets. So unlike things like, let's say you're trying to predict stock prices, or you're looking at the housing market, or you're trying to predict the weather, often you've got millions of data points that are just accessible at your fingertips. Even though that there are decades and decades of literature on reactions that have been done in the past, often these are fragmented through different journal articles, and if you're not using these data mining tools, it can be difficult to get a clean, large data set that you're able to kind of execute these AI technologies on. And even if you do have this perfect data set, I know that a lot of you are working on the cutting edge of material science. You're going to be doing reactions on materials which people haven't used before, and reactions which haven't been done before. And as such, you might get unexpected phenomena. You might get reactions or occurrences that are very difficult to predict, and the AI technologies just can't foresee what is going to happen. And in such circumstances, we need systems that are able to take feedback from the reactions that you are doing, to use the data that you already have to help supercharge your processes. So this brings me nicely onto the concept of a self-driving lab. So a self-driving lab is one way in which you can combine AI with automation to synergistically help you to develop new materials. And as I've mentioned, compared to the technologies on the previous slide, it's just one way in which you can use to develop your materials. And yeah, I'll show you how to do it on the next few slides. So before we go into a self-driving lab, it's probably useful for us to remind ourselves how materials are developed at the moment. Typically, you'll have a business team or a technical team, and then they will go to a researcher and tell them that we need this material that will unlock these new capabilities that will allow us to produce this new product. The researcher will then devise some experiments that they think might, hopefully, possibly make this new material, and then they'll go run those experiments. Once they've run those experiments, they'll do some analysis to see how close their materials are to the ones that they need to make. And more often than not, they will likely have to go through another round where they'll have to run more experiments, do more analysis, and then continuously go through this process until eventually they've made the material that they want. Now, as Professor Mary and some of my predecessors have mentioned, our AI tools can really help to accelerate this process. Rather than you having a researcher make these decisions, we can use one of these AI tools and tell it what you want from your material. You want a particular yield, you want a particular particle size, maybe you want a particular reflectivity or a particular strength, and then you tell it what levers you can pull. These are the concentrations I can change, these are the materials that I have, these are the pressures that I can change, these are the temperatures that I can change, and the AI algorithm will then devise the experiments for you. So we're currently still kind of like in this intermediary stage where we might need to run the experiments ourselves, do the analysis ourselves, and then take those back to the algorithm so that it can suggest the next round of experiments. But it's still far quicker than the previous stage where we have a human making the decisions here. The next stage of this is the self-driving lab, where rather than you manually conducting these experiments, the AI algorithm not only has control of suggesting the experiments, but it can also run the experiments and do the analysis for you. Because of that, then the algorithm can take control of the entire process. You can be at home, asleep, in bed at night, and the system can be devising experiments, running experiments, testing the material, and going through this optimization loop on its own so that it can create the materials for you. Here I've just got a simple example of how a system like this might work. So let's say you've got 3 ingredients, you're combining them together, you're heating them in order to make your desired material. The AI algorithm can then pick the flow rates of the pumps, select the temperature of the reactor, do the reaction, and collect the product in a bucket at the bottom here. Whoops. Oh, here we are, at the bottom here. What we can then do is take a small amount of our product, analyze it using this instrument here, and then feed the results to the AI algorithm. The AI algorithm can decide how it wants to improve the recipe and then have a second crack at the process. Again, it can collect most of the product here, do the analysis, and then just go through this loop iteratively until it's optimized the entire process. And we have quite a lot of benefits to doing things this way. With each step of the optimization process, we're using the data that we had before in order to influence our future decisions. These systems now are at the level where these things are not just a proof of concept. I've been doing this for about 10 years now, and these systems are reliable enough and robust enough where you can go home, you can leave them unattended, and you can go off and do other things whilst these systems are running. And because of the increasing power of these AI technologies, it's not just a case of having 2, 3, 4, or 5 variables anymore. You can have hugely complex, multi-step chemical processes, and AI systems are able to digest these and help you to reach your desired goals in a few number of experiments. So many of my predecessors have spoken about the AI technologies that you can use. So for today's presentation, I'll focus on the automation side to help you figure out how you can use automation to reduce the time and the effort needed to do your experiments yourselves. So step 1 is selecting the equipment that you need in order to do your experiments. Step 2 will then show you how you connect these devices together. And then step 3, you need a way to control these devices so that you can automate the entire process. So why hasn't this been done before? I think it's because lab automation can be quite difficult. When people think of laboratory automation, they think of very complex laboratory equipment, which is very expensive to buy, very expensive to install, and then very expensive to maintain. And a lot of the time, we've been working in manual environments. Our labs are 20, 30, 40, 50 years old. And sometimes it's difficult to imagine how these robotic technologies are going to displace everything that we've been doing in our labs for the past few decades. Compared to our previous instruments where we just have some scientists, engineers to operate our processes, these robotic labs often need additional expertise that we might not have in our labs. So in order to implement these machine learning and these robotic technologies, in addition to our chemists and our engineers, you might need an electrical engineer. You might now need a mechanical engineer. You might need a software developer. You might need a mathematician for the AI. And for a lot of us who are developing materials, we just don't have access to this labor. And sometimes when you're developing these automated systems, it can be quite easy for you to develop yourself kind of like into a bit of a hole. So at the start, you want to make your process as adaptable as possible, but then the more decisions that you make, the more rigid you make your process, and suddenly you can end up with a system that's very good at optimizing one process, but is not very good at doing anything else. And these are the shortcomings that I want to try to address with laboratory automation over the next few slides. So we're going to start off with equipment selection. The first thing that you need when you're trying to select the equipment to make a self-driving lab is something to control your reaction. And for those of you who are making materials out there, you're going to know what needs to be done here. If you need to heat your reaction, you need something that can heat it. If you need to change your pressure, you need something that can apply pressure. At each stage of this development process, I'll give you some kind of fancy technologies and then some easier technologies which you can use and adopt just using stuff that you're already likely to have lying around in your lab. So for reaction control, on the complex side, we could use something like a flow chemistry setup. So this is the schematic that I showed you a few slides ago that's kind of fully automated, and these things are great. You can easily modify temperature, you can modify concentrations, they're super safe, they're easy to control, but if you're trying to do anything with solids or you have very slow kinetics, then these systems are kind of out. Next, you could have a fully automated robotic system. So some of you might have worked with something like a ChemSpeed or something from, say, Unchained Labs or Unlimited Labs, and these things are amazing. They do absolutely everything. They'll make your dinner for you. They're fully robotic, they do heating, they'll do the analysis, but they suffer from some of the issues that I mentioned at the start. They're expensive to buy, they're expensive to install, they're expensive to upkeep, and if anything goes wrong with it, then you'll have to call the engineer out to fix it for you. My advice is start with something simple. Hot plate stirrer. It heats, it stirs, and for most reactions, that's all you need. Most of them have a USB port or a serial port at the back. Just connect it to your computer, and that's reaction control done. We don't need anything more complicated than that at the start. Even something simple like an oven or a circulator. If you're just heating your reaction, just send the tube through an oven. It's very stable. It might be a bit slow if you need to cool your reaction, but if you're just trying to heat your reaction and you've got nothing else, it's a great way to get started. I put circulators in there because I think most labs just have a cupboard that's full of circulators at the back that nobody's using. You can pull one of these out. Again, a lot of them have USB ports. You can plug them into a computer. It's a great way to get started. Okay, so you've got something that can do the chemistry. You've got something that can either do the heating or that can apply the pressure. If you're doing something like photochemistry, just something as simple as a UV lamp will work. Plug it into the computer via USB, and it will decide when to switch on and when to switch off. So step 2 is materials handling. We've got our reactor, and we need some way of getting our material into our reactor and out of our reactor when it's done, so it's ready for the next reaction. And there are a few ways in which you can do this. So the first of which is a liquid handler like this one. You just have like a needle, it can prepare your reactions, and yeah, mix your chemicals together. The thing is robotic, but just like the robotic systems I mentioned in the past, they can be quite difficult to program and they can be quite expensive. Next, you can have a robotic arm. So you just have like a simple pot of stuff, and the robotic arm will put it onto the hot plate. And when it's done, the robotic arm will pick it up and move it aside. Now, I know a lot of people like using robotic arms, and for people who haven't used robotic arms, it seems like a really versatile solution. But in my opinion, they can sometimes be difficult to program. Trying to get it to detect the flask and get it to pick it up can sometimes be a pain. And even though they seem very versatile, often you can only get it rigid, move this from here to here. It's not like a remote control, and it's not completely smart. It can't just do anything at any time. So kind of once your robotic arm is in there doing a particular process, that's it, it's locked in there. And my advice is, if you want to get started with something really quickly and really cheaply, just use a pump. Just have one pump going into your hot plate, have another pump coming out, your reaction material goes in, your reaction material goes out. 2 pumps, that's all you need if you want to get started quickly. Most of them, again, will have a USB port at the back of it. You can connect it to your computer, and you can get started really quickly. Right, next we've got a sampler. So as you know from the process, once your reaction is complete, you need some way to analyze your material. So once the reaction is complete, we need some way of getting our product from our reactor and into this piece of analytical equipment. And this is the step that I think that's most difficult for people who are just starting with automation, because it's the type of equipment that you probably haven't used in the past. It's going to have to be slightly robotic. But even then, there are simple ways to go about it, and there are complex ways to go about it. So the first thing is an in situ sampling probe, and I only used one of these quite recently. They're super versatile. It's just like a probe, and you can either put it into your flow setup or into your pot. And it just has like a little suction thing at the bottom, and it'll just suck up a small amount of your reaction material, and then you can fire it off and send it off to some piece of analytical equipment. I didn't know they existed, but I've used one now, and they're actually really good. Robotic arms and liquid handlers I've already spoken about. But my advice is the simplest way to get started is just a valve. So imagine you've got your hot plate, you've got your pump which is pumping material out. You can just stick a valve in the middle, the valve will switch, and it can just send your material to your piece of analytical equipment. And it will just have one command: switch the valve on, switch the valve off. Super easy to control. And finally, we need something to do our analysis. Now, this is something that is difficult for me to prescribe to you because you're all going to have very different objectives from your materials processes. Some of you might be wanting to optimize for size, some of you might be wanting to do it for shape, some of you might be wanting to do it for thermal stability, some of you might want to be doing it for some electrical conductance, you might be making semiconductors. You guys in your respective fields will know what piece of equipment is best for the chemistry that you want. The only saving grace and the positive thing that I can tell you is that industries are becoming more wise to people wanting to do automation. Whereas previously, these manufacturers had locked their pieces of equipment down, now there is an increasing push for open communication protocols, for interoperability between pieces of equipment, and there's a good chance that if you've bought your piece of equipment within the last 5 years, within the last 8 years, it's going to have some ability for you to connect it to a computer and some ability for you to control it. And with anything that I've mentioned here, if any of you have any questions or you want to automate your own pieces of laboratory equipment, get in touch with us. At the University of Cambridge, we've done this. We have quite extensive experience with this, and we do want to kind of promote this. So yeah, do feel free to ask us. So once we've selected our equipment, the next step is to connect it together. And in this step, this is physically how you connect your devices together. We'll worry about controlling them in the next step. So there are complicated ways in which you can go about this. So we've developed like really complex systems where we've got one system in Singapore, one in the UK, the things are talking to each other, and one's doing one step, one's doing the other step. If you're just getting started with this, this is probably going to be likely too complex. My advice to you is just get one computer, one laptop, and just plug everything into the USB ports. It's the simplest way to get started with this. Anything afterwards, if you get past that step, fantastic. And when you're thinking about connectivity, I think sometimes people get confused between the connectivity protocol and the physical connector. So my advice to you is, for the first step, just worry about how to plug this thing into your computer. You can worry about how to control it in the next step. So if it's something like USB or Ethernet, you can just plug it straight into the computer. For anything else, there'll be some adapter on Shopee. You can just buy it, put the adapter, put it into your computer, and just move on to the next step. So yeah, that brings us nicely onto this third step. How do you control your devices? So I'm a bit limited on time today. I did have a whole series of steps on how you can go about the various communication protocols for controlling your devices. I took the slides out here, but my advice is, if you've got serial communication, go with that first. It's super easy. The next one is Modbus. It's basically like serial, but your commands are standardized. And then the last one I can mention is OPC UA. It's a new open communication protocol. Most of the device manufacturers are following it, and it's really easy to implement with all of the technologies that I'm going to mention on the next slide. So yeah, I've mentioned kind of 3 communication protocols, and then you can decide how you want to implement it. And the list is by no means exhaustive, but it provides a good place for you to get started. So Python is utterly amazing. And people think that Python is just for data scientists, but we've got reasonably complex stacks where we have a whole range of hardware, a whole range of machine learning algorithms. There's a front end, there's a back end, there's orchestration. The whole thing is done in Python. So if you're kind of like new and you're starting off in these technologies and you think you have to learn 10 languages, if you've got somebody who knows a bit of Python, that's enough for you to get started, and you can build something reasonably comprehensive with that. MATLAB is pretty good because I know that a lot of engineers are taught MATLAB during their university times, and it's something that people already have a lot of expertise on. The only limitation is that you have to pay for it. LabVIEW is really good because it already has support for a range of devices, and I know that a lot of laboratory manufacturers support it. If you go back about 10 years, if you wanted to control laboratory pieces of equipment, LabVIEW was the only way to go about it. But now that device manufacturers are supporting open communication protocols, like OPC UA, like Serial, if you are able to code in Python, that would probably be my suggestion. Yeah, so in order to build your lab, it's just a case of selecting your equipment, putting it together, plugging it into the same computer, and then just pick one of these technologies in order to identify your communication protocol. So this brings me nicely onto AMLearn. So AMLearn is our proprietary product for helping you to do automation and machine learning in the laboratory. So it consists of a Python-based orchestration layer. And as I've mentioned, the Python handles everything. It will handle your device communication. It will handle like offloading things to the database and everything that you need to do in order to build a self-driving lab. We have our own adaptive machine learning algorithm that we've developed at the University of Cambridge that will take care of all of the decision-making processes. And I know that some of you here might be engineers, but a lot of you also might be scientists. And I know that for chemists and material scientists, anything remotely related to code can be quite terrifying. So everything is completely done through a no-code interface. And yeah, our plan was for it to be as easy accessible and reduce the barrier to doing laboratory automation. I do want to spend a little bit of time talking about the algorithm. So rather than just doing continuous variables, it also helps you to do discrete variables. So previously in the presentation, I mentioned that we have this need in order for systems to understand the difference between various chemicals. Let's say you're doing an optimization and your three solvents are ethanol, methanol, and hexane. If the system has used ethanol, you want it to understand that methanol is unlikely to work well and move on to hexane. This is where descriptors can work really well. What we do with AMLearn is that in addition to the statistical algorithms, we have an AI agent that's running quantum mechanical calculations in the background, and then the two are working together to synergistically help make the decisions in the process. A lot of you will know that there are a range of models that you can use to optimize your processes. And I guess this is some advice for those of you who are also looking to implement some AI technologies into your work. Oops. So neural networks are great. I know that there is this misconception that you need kind of thousands of data points to use neural networks. But in our experience, if you set the neural networks up well, and we can give you some advice on this, even if you've got 30 to 40 data points, you can really start to make really reliable predictions using neural networks, and particularly if you've got quite a complex process with multiple steps, multiple chemicals, pressures, temperatures, times, these really complex processes with like 30 or 40 variables, the neural networks are fantastic at this. But also, you don't want to be using a sledgehammer in order to hammer pins. So if you have a multi-objective process where one of your objectives is very complex, like doing this multi-step optimization, whereas another one is quite simple, such as reducing the cost of your optimization, it's better off that you use a simpler model that is much faster, able to optimize with much less data. And the nice thing about AMLearn is that regardless of what kind of objective you have, it will decide what the best model is for a given optimization problem and make that decision for you. As a chemist or as an engineer, you don't have to make this decision. Finally, any of you who have done machine learning or done any of these AI technologies in the past will know that it's not just a case of spinning up a neural network. Anytime you load up any one of these packages, it's going to ask you, how many layers do you want? How many nodes do you want? What activation function do you want? And for those of us who are kind of scientists and engineers, we're not going to have answers to these questions. And these answers might be dynamic. For a given problem, you might have the settings as one set at the start of an optimization, and the figures might change later during an optimization. And it's up to the chemist to know what are the best parameters and how they're best to change during an optimization. And the nice thing is that our software will take care of all of that for you. You don't have to worry about it. At each step of the optimization process, it will constantly look at your problem and constantly tweak the parameters so that your machine learning strategy is optimized for your given process. So you might have various pieces of equipment from various manufacturers around the lab. And in the time that we've been operating over the last 7 years, we've optimized most various different pieces of lab equipment, whether it's something simple like a pump or a hot plate, or something quite complex like, say, a ChemSpeed or a Vaportec system. We have comprehensive device support, and we have device support from a range of various manufacturers. And the process is quite simple. You just install the software, plug in your pieces of equipment into this one computer, and you can get going doing the kinds of machine learning workflows that I mentioned in my previous slide. And this is kind of like what it looks like in the software. So you just start off and you kind of just tell it what your objectives are. So you might want to maximize yield and minimize cost. Anything that you can assign, oh, this is another piece of advice for you guys actually. Sometimes people think that you can be a bit mentally limited by thinking what these AI processes can optimize. If you can assign a number to it, the system will be able to optimize for it. So if you want to improve the greenness of your system, just add a score to each of your solvents, maybe add a score to the heating. If you want to reduce the temperature, add up those scores at the end of the reaction, give it to the algorithm and tell it to reduce the score. If you wanted to reduce the cost, just tell it the cost of your reagents, multiply it by the concentrations, throw it into the algorithm, it will help you to reduce the cost. Anything that you can quantify in any kind of way, my advice to you is, whether you're using our system or something else to optimize your processes, the only thing that limits what the optimization can do is your imagination and your creativity. And it's the same with the variables. So sometimes we just imagine things in the laboratory as being our variables, like pressures, temperatures, times. Let's say you're doing a robustness study. Let's say you have 10 operators and each of them is getting a different yield. You can put that into your optimization and figure out what is going on in your process. And again, the system is only limited by what you want to put into it. Step 2 will be you just tell the system what resources are available and how many reactions it is that you want to do. This is kind of just like a checklist, just to check that you're happy with the reactions that you want to do. And then step 3 is just setting up your automation protocol. So just as I mentioned at the start, the system will tell you all of the devices that you have available, and then you just give it the steps that you want to proceed through. First start my pumps, then start heating my reaction, then take an analysis using the HPLC, then extract the peaks, then calculate the yield. So for each step of the optimization process, these are the steps that it will go through. And yeah, this is the kind of like the final message that I want to leave you with. And I think it's the message that a few of my predecessors have echoed. These AI technologies are amazing, but they're only limited by the data that we have available. And if you're doing something cutting edge, you're doing something novel, you're doing something that the existing AI technologies can't do, just provide it with your own data. Whether you're doing it manually or whether you're doing it robotically, I think it's the synergistic use of AI and experimentation that's going to kind of unlock the next series of developments in materials discovery. But yeah, thank you very much for listening. If any of you have got any questions, you can email them to me. And yeah, thank you very much for listening.
Ladies and gentlemen, a very big round of applause for Dr. Mohammed.
Oh.
Thank you very much.
Oh.
We will see you, of course, downstage for all the questions. And ladies and gentlemen, I hope you had a great time listening to Dr. Mohammed. Thank you. Can we give him a round of applause again? Thank you for the excellent presentation and rounding up the day for us here at Switch 2025, Singapore's Week of Innovation and Technology. That does it, ladies and gentlemen. I believe that we still have a masterclass that's still ongoing at the back. If you'd like to hop in right now, I believe it's going to end around 4:35. If not, I hope you had a great day with us talking about AI. This morning, Mumfai was there to open. And of course, we changed track, of course, from the afternoon onwards. My name is Sue. I hope to see you here again tomorrow for our community day, which is going to be from 9:30 a.m. onwards. So please mark it down on your calendar for Beyond Stage, and we welcome you back for day 3, the very last day of Switch 2025. With that, if you're headed back home, have a safe journey, and we'll see you here tomorrow at 9:30 a.m.